Okay, so hello everyone. The plan for today is to discuss independent component analysis, and then we will see how much time we have. If we have time, then we will talk about simulated annealing, which will be our first algorithm that is designed to do optimization over non-convex functions. Okay. If we don't have time for that, then we continue next week. Okay, and other announcement that I went to bed at 9 a.m., so technically I'm still sleeping. So if I fall asleep more, then maybe some of you can continue. So independent component analysis. This is the problem that we have x1 and x2, and we can have more observations, and we have S1 and S2 independent sources. And we mix them linearly with, as you can see, with A11, A12, A21, A22 coefficients, and we got these observations. So we can observe only x1 and x2. And the goal is to estimate the original signals. So in this case, the original signals look like this. This is S1, this is S2. We can observe only these quantities, x1 and x2, and the goal is to estimate these quantities, and we will see algorithms that can recover sources like this. Is it clear what we want? Okay, so formally, oops. This is our model that we have say S1T, S2T. You can generalize this even or to have more independent sources. We observe, we don't observe these quantities. What we can observe is a linear mixture. Say x1t is A11 S1t plus A12 S2t, x2t is A21 S2t plus A22 S2t. This is what we observe, and we want, so say for, I don't know, T1 capital T, and we want to estimate S1T and S2T. So we want to estimate S1 and S2 from which one?
Row number 4.
A21, A22. Oh, right. Good. I'm sleeping, I told you. So. Thanks. Okay. So this is our goal. And we also want, say, the coefficients, Aij, from the observations. Okay, the problem is that we don't know these coefficients Aij and Sit. So an explanation of this problem is the cocktail party problem, that imagine that there's a room, and in that room there are many independent sound sources. So you are talking to your friends, and there are some microphones there, and those microphones can record mixed sources. Or say, imagine that in a room there's an ambulance car. If I can press it. Right? Or the TV is on. Someone plays the violin. And your rock band is also in the room. Okay, but we cannot observe these. What we can observe with microphones is the mixture of everything, right? So we have 4 microphones in this case. Right, and this is the 4th. Okay, so the question is that we have these observations and how to estimate the original signals. So ideas, so if you know ICA, then of course you can say ICA, but so what would be good principles for that? Right, so how this problem looks like is that we have it's a matrix factorization problem. We observe X quantities. We can arrange them in a matrix. And we know that X is a mixture of A times S. We don't know A, we don't know S. So we need a matrix factorization algorithm. And one matrix factorization algorithm is the PCA, principal component analysis, that you all know, right? Right, so you might try to do what PCA would do if run on this data set, and here are the results. So it's not that promising so far. And the plan for today is to learn algorithms that can recover sources like this. So here we use the so-called fast ICA algorithm for that.
Long list of American fast foods that have successfully made the long march to Asia, from Seoul to Singapore.
And this is the 4th. So formally the problem that we have independent sources, ST. So this is S1, S1T, S2T, S3T, S4T. We have a mixing matrix A. And we mix S with the mixing matrix A. So XT is A times ST. We observe X. We want to estimate A and S. And what we are going to do is that we are going to look for a matrix W. We observe XT, and we are looking for a matrix W, such that in ideal case, this W will demix these sources. So for example, if W is the inverse of A, then YT, our estimated signals, would be the original signals. So the question is how to find a good W. And so this problem is interesting because so far, so we will see cost functions, and we need to optimize those cost functions where the argument is W. And many of those optimization problems that we learned so far, they were on vectors. But here, W is a matrix. So it's similar to SDP in that sense that there our objective was over matrices, and similar thing happens here. Okay, so we will need a couple of some theoretical statements. So first is what we mean on independence in this case. So we had independent sources, we mix them, and we want to demix them, right? That's our plan what we mean on independence. So say y1 and y2, they are two random variables. So I'm asking you, what does it mean that they are independent? Anyone?
Joint distribution of factors to the
Right. So say if they have densities, then py1, py2 is the product of the marginal densities. Okay, we will need the Shannon entropy as well. You all know this. That is, say, the joint entropy of, I don't know, we have m random variables. Then this is minus p minus p log p, the integral of minus p log p. And we also need the Kullback-Leibler divergence, the definition of that at least. So if we have two densities, f and g, then the Kullback-Leibler divergence between them is integral f log f over g. And we know that it's non-negative. And this is 0 if and only if f equals g. In the homework 5, you might play a bit more with this, and you might need to prove a couple of other properties. And what is mutual information? So who has never heard about that? So you all know. So then someone, the definition of mutual information? Oh, okay. So then the definition of mutual information? Okay, then someone else. So mutual information. So what's that? So we need to measure dependence between y1, y2, ym, and we will use mutual information for that. But what is the definition of that?
h of a minus h of a given b, for example, like if a and b are
Right. With Kullback-Leibler divergence? Right. So Kullback-Leibler divergence measures how far two densities from each other. We know that y1 and y2, they are independent if and only if the joint is the product of the marginals. So let's measure how far the joint is from the marginal, product of the marginals. And that's the mutual information. Oops. So the mutual information between y1, y2, ym is the Kullback-Leibler divergence between the joint density and the product of the marginal densities. Okay. So we know that that's clear so far, right? We know that this y, it's w times x. W is a matrix. We are looking for that. And if the mutual information of this y becomes 0, we are happy because it means that our estimation, the components of our estimation, they are independent again. The difficulty here is, though, that we need to estimate the mutual information, and then we need to minimize the mutual information in W. And so questions how to estimate this mutual information. So how would you do that? So you have samples, many samples. For each given W, you have samples from these y random variables. But the goal is clear, right? We estimate the mutual information, then we minimize it.
Can we just estimate the covariance matrix based on the samples that we have, and from that we have everything, like we have all the...
Right. So the problem, so you mentioned covariance matrix. You can measure mutual information with covariance matrix if and only if the random variables are Gaussian. If they are not Gaussian, then just estimating covariance matrix from the samples won't be enough to estimate mutual information.
And do empirical averaging?
Of what?
Just the samples.
So we have,
Replace that with some.
right, but what would you put here? Or here? Or here? Right, you are right that we could replace this with empirical average, this part, but we need densities here. Right, so a naive approach is that you density estimation first. You estimate the density of this joint distribution. You estimate the density of this, estimate the density of this. You plug that in, calculate this integral, and you do optimization. But the problem with this approach is that if you have, say, hundreds of random variables, then you need a 100-dimensional density estimation. And for that, you would need exponentially many sample points. So that's not a very good approach. Right? So it almost looks like that this problem is hopeless. And still, there are IC algorithms that can solve, and they can separate, say, 200 mixed independent sources. Right? So you might wonder how they do that at this point. Questions? Okay, so formally the problem is that this is the ICA problem. X equals A times S. X is the observation. A is a mixing matrix. S, S1, S2, Sm, they are jointly independent random variables. And we have a theorem first which says that these S1, S2, Sm independent sources, they can be recovered only up to sign, scale, and permutation. So we have no hope to recover the sign of S1, the scale of S1, and if we permute these independent sources, they are still independent, right? So this is trivial. So here is a formal proof. If P is an arbitrary permutation matrix, lambda is an arbitrary diagonal matrix, then lambda times P times S as a vector, the components of these vectors, they are still independent, right? If I have S1, S2, Sm, they are independent. If I permute them, they are still independent. If I rescale them, they are still independent. And I could put this lambda and P scaling and permutation matrix inside of this mixing matrix. So just from these observations, I have no way to tell whether the mixing matrix was A or this, and whether the original sources were S or this. Okay? Another observation is that we can assume that the expected value of S is 0. Why? It's very simple, because you could, so you make your observation X, you could remove the expected value of X, and then you would get this equation. And here it's again a linear mixture model with the same mixing matrix. So you can assume that the mean of your hidden variables S, they are 0. Okay, the other assumption we will make is the covariance of this random variable S is the identity matrix. We know it's diagonal because they are independent, and we just discussed that we cannot say anything about the scaling, so we will just assume that the covariance matrix of S is the identity matrix. Okay, so these are the two assumptions. The covariance matrix of S is the identity matrix, and the expected value of S is 0. Okay, another trick that we will do is called whitening. Have you ever heard of that? Right, some of you. So what it does is the following, that we have quantities X, right? And let matrix sigma be the covariance matrix of X, which is because we assume that its mean is 0, it's the expected value of X transpose, which is, we know that X is A times S. So this is the expected value of A times S, S transpose, A transpose. What's this? A transpose, right? Because the expected value of S transpose is the identity matrix. And now what we do is we do a singular value decomposition on this matrix A. Sorry, on this matrix sigma. So that's U, say D, U transpose, where U is an orthogonal matrix. We have M independent sources. So S is S1, Sm. So in other words, U contains the singular values, and D is a diagonal matrix with rank M. Okay, so we do this. So you observe your quantity X from that you calculate the empirical average, that's sigma, and you do a singular value decomposition on sigma. That's UDU transpose. And then what you do is that you say that let matrix Q be defined as the square root, inverse square root of D U transpose. Which sizes are to the M times N, where we assume that again we have M independent signals and we have N observations from them. And let A star be defined as Q times A. Okay, so now I can define new X star variables as Q times X. So we had the original observation X. We just calculated this quantity Q, and I multiply all of my observations with this matrix Q. That's X star. So X star is Q times X, which is Q times X is A times S, right? And I will just say that this matrix is A star. So now I have a new ICA problem where the original independent source is S. They are the same, but I have a new mixing matrix A star. And why this is good for us? Any guess? We can even say more for. But you are right that the expected value of X star transpose. So what is this? Is the expected value of QX X transpose Q transpose. This is Q. This is sigma, you remember, the expected value of X transpose. And Q was defined by this, and sigma is U du transpose. So if you plug this here, you plug Q here, then what you get is that So that's Q, we have U, D, U transposed, and we have Q transposed. And what is this expression? U transpose U is the identity. So this is identity. So what we have is that for the covariance matrix of X star is the identity matrix. And we also have that A star transpose is again the identity matrix. In other ways, the mixing matrix is orthonormal. Okay, so if you do SVD on the covariance matrix of your original observations, you calculate this matrix Q. After this, we reduce the problem to another ICA problem where the mixing matrix, now we know that it's orthonormal. It's not an arbitrary matrix. And why it's good? Because if we have a, say, n times n, I use them, but anyhow. So if we have a n times n mixing matrix, that was the original problem, it has n squared free parameters that we need to estimate. But if we have an orthonormal matrix, then it has half of those parameters that we need to estimate. Okay, so let's see how this looks like when the original sources, they are just uniform. So we had uniform distribution between -1, 1. This is S1, this is S2. And the mixed sources will look like this. If you mix it with a 2x2 mixing matrix, and I plot our observations, they would look like this. And the whitened sources will look like this. So after this, what we need is just to find an orthogonal matrix, a rotation in 2D, with which we would get, again, the original sources. Is it clear so far, everything? So what you can see from here that, so here S1 and S2, they are independent. This is just the rotation of that. So the covariance matrix is the same. So the covariance matrix of these observations is the identity matrix. But now X1 and X2, they are not independent from each other. Can you see that why they are not independent? What's the intuition? So the intuition means that if you know, say, X1, it would tell you information about X2. Here, if I know S1, it doesn't tell me anything about S2. But here, if I know, say, X1 is this point, that tells me that X2 is this. So they are not independent anymore. Okay, so this is what we have done so far. So ICA task, we are given observation X. Our goal is to find the Y, the estimation of S, and find W matrix, which will be the estimation of the inverse of A. We will use this model that Y is W times X. And for preprocessing, we remove the mean from our observation X. We did whitening, so we assume that the expected value of X transpose is the identity matrix. And now all we need is to find an orthogonal W that will minimize the objective function, say the mutual information. Right? So after this, we just need to find an orthogonal matrix that would rotate this back to this. So we will discuss soon the cost functions, but generally if we have not two, but we have, I don't know, m independent sources, then we need to find m times n orthogonal or orthonormal matrix. So we have a cost function, and we want to optimize that cost function over orthonormal matrices. Generally, a sometimes very useful idea is if you decompose that orthonormal matrix as a product of simpler orthonormal or rotation matrices. And these are called, here they are called Gibbons rotations or Jacobi rotations. I don't know if you have heard of that. But the point here is that you can see how one simple rotation matrix looks like. And if you, so for each P and Q, you have a cosine and sine, or minus sign. All in the diagonal other than that we have ones, and all others are zeros. So it just mixes two coordinates, right? And if you have an arbitrary orthonormal matrix, then you can decompose that as a product of many of these orthonormal matrices. So what you can do is that you have your ICA problem, you have your cost function that we will discuss a bit later, and you just try to decompose that. Say you try to decompose the first and second coordinate. So you will just optimize in theta, where we just mix where P is 1, Q is 2. Then you choose Q to be 3, then Q to be 4, and so on, and then you increase P to be 2, and so on. So you choose all possible pairs, and for all possible pairs, you optimize in theta. So it's like a coordinate descent algorithm. Okay, so the point here is that even though orthonormal matrices might look ugly, you can decompose the optimization problem to simpler optimization problems. And there are many ICA algorithms that uses this trick. One of them is called radical, that works very well, and that uses this approach. Is it clear? Questions? Yep.
We assume the number of sources is the same as the number of.
Oh, very good point. So question is how many sources and how many microphones we can have. And what we will assume always here is that you have more microphones than sources. Okay, if you have less microphones than sources, it will be very difficult to do anything, because what you do is that so say you just have one microphone and you have 100 of signals, then you need to estimate all those 100 signals from one observation. But because you do a projection, you lose information. So it's very difficult, and it's still actively researched in ICA what to do in those situations. So what we will assume that if you have, say, 3 independent sources, then we have at least 3 microphones. Okay?
But
Right.
Another question is, this is a non-convex optimization.
Exactly.
So are there any guarantee that this coordinate descent kind of?
In this way, no. But there are some novel results on other formalization of ICA where they have guarantee, but not with this approach. But still, in practice, it works very well. Right.
So in previous slide, S1 and S2 were uniformly distributed, and we had a rectangle. So
Right.
they are Gaussian. So we have a sphere.
Oh, that's another good point. So what can we do if we have Gaussian sources? So say I have 2 Gaussian sources. So they are independent, okay? And let's mix them with an orthonormal matrix. What would happen?
Any rotation is a solution.
Right, so what happens here is that if you have if you have 2 Gaussian sources, jointly they look like a 2-dimensional Gaussian sources with identity covariance matrix. You rotate them, they will look the same. They are still independent. So for Gaussian sources, even after mixing with orthonormal matrix, they look the same. They are still independent. So for Gaussian sources, it's very easy to make them independent, but you have no hope to recover the original mixing matrix, because for each rotation, they look the same. And you might ask the questions, what are other sources, what are other distributions where we have the same problem that we cannot estimate the original mixing matrix? And you might say that, hey, if we have a spherically symmetric distribution and I rotate them, it will look the same, so we have the same problems. So you can say that with ICA, we cannot recover those independent sources whose joint distribution is spherically symmetric. But you can also prove that if you have independent sources whose joint distribution is spherically symmetric, that's Gaussian. So the Gaussian distribution is the only distribution there where we cannot recover the mixing matrix. You might assume that you have one Gaussian distribution among these, but you cannot have two. If you have two, it's easy to make them independent, but again, you just cannot estimate the mixing matrix. Soon we should have a few minutes break. Right, so let's have a very quick break, and then we will discuss ICA cost functions and then algorithms. Okay, we have many things to discuss, so it will be 2 minutes. Cost functions we can use, and we already discussed that one cost function is mutual information. The only problem with this is that it's very difficult to estimate, right? And we also know the definition of entropy. So if we have y m-dimensional random variables, so its components are y1, y2, ym, then its entropy is defined by this expression. So there's one lemma that you can prove that the entropy of w times x, where w is a matrix, say m by m matrix whose determinant is not 0, so the matrix is invertible, then you can prove that the entropy of w times x is the entropy of x plus the logarithm of the determinant of w. Did you know this? Who didn't know that? Right, so if you have never seen this, then think about the proof. The proof is not difficult. So especially in one special case, if say w is just a scalar, then you should be able to prove it in a minute or two.
Is the second term the capacity of the channel? I mean, if x is
I couldn't hear the second term.
if x is the source and wx is the, I mean, your communication system is what we got.
Right.
Yeah. Then the second term does that mean the capacity of the channel?
Of the channel?
Yeah.
Right. I'm not sure, so I should think of that. So that's true that mutual information has a strong relation to this, like channel capacity and so on, but I'm not sure if in this context is that. But anyhow, so this is, you can prove it with integral transformation. So for now, let's just assume it's true. Okay, but if you believe this, then here is how we can proceed. So the mutual information between y1 and ym, sorry, so sometimes I use capital M, sometimes not. So the mutual information between these random variables is, by definition, is this expression. And now what we can do is that y, so I can, because of this logarithm, I can decompose this as the integral p log p with this. That's the negative entropy, plus integral p log 1 over these guys. But because of the logarithm, they will be additive, and the integral of p joint distribution log 1 over p marginal distribution, it will be the negative entropy. Right? And we just add this. And now what we can use here is this lemma that was the entropy of y1, ym. So this is y. It's just the entropy of x plus logarithm of determinant of w. So I plug this guy here, and I got this. So the point, this was our original cost function. The variable we want to minimize is w. There's no w here. So this is constant. There's w here, and these guys depend on w as well. But hey, they are just the entropy of one-dimensional random variables. So you just need to estimate entropy in one dimension, not in m dimension than here. So in the independent component analysis problem is equivalent to estimating the sum of one-dimensional entropies. You don't need to estimate mutual information of m-dimensional random variables. Okay, so as we discussed, this guy is constant, logarithm determinant w is 0. So because of that, this is also a good cost function in independent component analysis. So what we need is to minimize the sum of the entropies, right? Here. And we also assume that the covariance matrix is fixed identity matrix. So now the question is, if you fix the covariance matrix to identity, what is that distribution that has the largest entropy? So the covariance matrix is fixed. Okay, so forget that. So what's the distribution that has the largest entropy generally? If you're uniform, Gaussian. Right, my question is a silly question. There's no such thing, right? So you need to say some constraints because otherwise you could go anywhere with entropy. But if you fix the covariance matrix, then you can prove that, say, the covariance matrix is the identity. Then among all distributions, the Gaussian distribution will have the largest entropy. Here we want to minimize the sum of the entropies. So what we have is that we want to go far from Gaussian distribution. We are looking for a W that makes the distributions very far from Gaussian distributions. Okay, and here is another explanation of the same thing. If you, so we have, say, S1 and S2 random variables. They were independent. So they say they were uniform. If I mix two uniform distributions, this will be their density. If I mix three uniform distributions, this will be their densities. If I mix, say, I don't know, this is Laplace distribution. If I mix two of them, this will be their density. If I mix three Laplace distributions, this will be their densities. Right, so from central limit theorem, if you remember that, what happens if you mix independent sources, they will converge to Gaussian distribution, and that's what happens here. So that's why it makes sense, if I want to recover the original independent sources, I should go far from Gaussian distributions. Okay, so let's see a couple of IC algorithms after this. So let's assume for now that we know the densities of the independent sources, S1, S2, ST. Just for fun and because in this case our life is simpler. So in this way, this whole problem is just a maximum likelihood estimation. I know the densities and I need to estimate the parameter A. So xt is A times st, st is w times xt, where A inverse. So I want to estimate w, and which is the inverse of A. So the log likelihood function looks like this, sum t1 to t. So Px is the density of random variable x. And I also know that xt is A times st. So what I want now is to rewrite so I could even write that what's x? X is A times s. Oops. I want to rewrite this expression in terms of PS. So I know the densities of S. How can I do that? Do you know how it looks like? So you know the density of S, you know the density of PS1, PS2, then the joint density of PS1, S2 is just the product of these. And now I'm interested what's the density of A times S. So you know the density of PS, what's the density of A times S, AS. So my question is, what's the density of A times S at a point U? So you can prove that this is A inverse PS at where? A inverse U. So is it known or? So it's just integral transformation. Right. So right. Okay. So let's see just very quickly. So why I wrote A inverse U here? So U equals A times S. From that, S equals A inverse U. That's why I wrote that here. And what is this guy doing here? A inverse. So to see that we indeed need this A inverse here is you just calculate this. So integral of this density over the whole space it's a density, so it should be 1. Right? And as we discussed, U is oops, sorry. So let me go the other way. So we know that this is 1. I want to prove that I just need to prove that integral A inverse PS A inverse U du this is 1. Right, exactly. So that's what happens. So that's called integral transformation. So this is just the determinant of this linear transformation, right? So what happens here that I just substitute this with, say, Z. So A inverse U is Z. From that, du is A inverse times dz. And A inverse U is Z. So du A inverse. Oh, I'm sorry. Right. Good? And that's what you plug in here. So if you put this du here, then this A inverse and A will cancel each other, and you indeed got one. Okay, but let's move on. So if you have more questions, come to my office hours, where you can get candies too, and we can discuss this. So the log likelihood now is some log A inverse PS ST so A inverse is W, and because of the log, I can decompose this, that it's T times I'm a bit sloppy because actually we would need determinant here. So it's whenever I say log A inverse, I mean logarithm of the determinant. So logarithm of T times logarithm of determinant W plus some T. And so this is why we did this whole thing, because the components of S, they are independent. So this is just the product of P Si at SIT. And because of the log, this product becomes sum. So sum T equals 1. Oops. Log PSI, where SIT, what's SIT? It's say WI X T, where WI is the ith row of W. So I could just say, if I write, it's a bit ugly, so I just rewrite this as FIWI XT. So the whole point of this calculation might look a bit ugly, but what we did is just you do this integral transformation, and PS is the product of one-dimensional densities, and this is what we got, and we need to minimize this in W. So let me just rewrite this again, what we had. So we have T samples, we have M components, so this is what just we proved in the previous slide, and we need to minimize this in, maximum likelihood estimation. We need to maximize this in W. Right? So what can we do? We calculate the likelihood of L with respect to W, which is T times. So here is my first question. You might know this. What's the derivative of logarithm of determinant W with respect to W? I'm wondering if you have ever seen that. What would be if W is a scalar, positive? What's the derivative of logarithm W if W is just a scalar? Right. So from this, what's your guess? What will be the derivative of W inverse, right? Almost. So the only difference is that it's T times W transpose inverse. Plus some So let's calculate the derivative with respect to the ij's components. G. Oops, I lost the sum. Okay, so what's the derivative of this? So it's the derivative of log. So from that we have 1 over f k w k x t. And what do we have here? It's the derivative of fk, right? At this. Oh, I'm sorry. So you can, I'm really sleepy. So we want to calculate the derivative of this sum with respect to wij. Right? But it means that lots of terms become 0. So we don't have this sum. There will be only one term that's not 0, and that's the ith term. And we need to multiply this with what? So I'm calculating the derivative of this with respect to wij. So I need to calculate the derivative of this with respect to wij. So because of that, I need to multiply this with xj t. Is it clear? So we have this sum. I need to calculate the derivative of this sum with respect to wij. There's only wij is only those wk vectors where k is I first. So there will be only one term. Because of this logarithm, the derivative of this is 1 over fi. I need to multiply this with the derivative of f, so that's here. And I need to calculate the derivative of this with respect to wij, and because of that, I will have xj t term from that xt. Okay, so if you put all these things together, what we have is t times wt inverse ij plus sum t equals 1 to t Ta-dam. So in other ways, so this is what we got. So it looked a bit, the calculation looked a bit ugly, but the final result is just one line, that you update w with this rule that it will be proportional to w transpose inverse plus, so I divided this whole thing with t, plus 1 over t, sum t equals 1 to t, and let g denote fi, the derivative of fi over fi. This expression is w times xt multiplied by xt. Oops, sorry, xt. So component-wise, it looks a bit ugly, but if you put things together, if it's too fast, you can check at home that you will get this line here. Right, so if we assume that we know the densities of the sources, they are known. But you are right, in practice, we don't do that. We don't know that. And the interesting thing that many times, even if you don't know, you just guess something, it might still work, this rule. So that's called the maximum likelihood IC algorithm. Okay, let's move on because I want to talk about something else that's more exciting. So another cost function that you can do is called, instead of entropy or mutual information, it's called kurtosis. So again, our motivation, we want to go far from Gaussian distributions. For Gaussian, so the kurtosis is defined as for a y random variable as the expected value of the fourth moment minus 3 times the expected value of y squared, and this whole thing is squared. And we assume that everything, the covariance matrix is 1. So because of that, the expected value of y squared is 1. So this whole thing here is 3. And you can prove that for Gaussian distribution, the kurtosis is 0. Okay? And we want to far from a Gaussian distribution. Because of that, you want to either maximize or minimize the kurtosis. You just don't want to be in 0. This is Gaussian distribution, its kurtosis is 0. If the distribution is sub-Gaussian, it has a y tail, then the kurtosis is negative. If it's peaky like this, then the kurtosis is positive. Okay, we want to go far from 0. And let's discuss quickly the fast IC algorithm in 10 minutes. So our whitened data is denoted with Z, and we want to estimate the first ICA component. Hello. So again, our whitened data is Z, and I just want to estimate one component, one independent component. So I'm looking for a W vector with which Y will be W transpose Z, and I want that Y to be, say, S1 or S2 or any independent component. But I'm estimating only one this time. Okay? You can also think of this W as the first row of your original mixing matrix, which was an orthogonal matrix as we discussed, and because of that, the norm of W is 1. So W transpose, as I wrote here, you can think of that as the first row of W matrix that ultimately we want to estimate. So we want to estimate an orthogonal matrix. Let's just estimate its first row first. And we want to maximize the kurtosis. As we discussed, we want to be far from Gaussian. For Gaussian is 0. Let's maximize it. So the kurtosis is defined as the expected value of the fourth moment minus 3. And we also have this constraint that W, the norm of W is 1. So what can we do? Newton's methods, right? So at the optimum, when this is maximum, we know that the derivative of f plus some Lagrange multiplier multiplied with the derivative of h, that will be 0. So what's our kurtosis is function f, right? So the derivative of that is 4 times the expected value of y to the 3, but y is W transpose Z. So that's this expression, and we calculate the derivative with respect to W. That's why we have this multiplier here. The derivative of W transpose Z with respect to W is Z. And the derivative of W transpose W is 2 times W. So we are looking for a W vector with which this holds. So I can estimate these from my samples for each W. And lambda is a Lagrange multiplier that we don't know yet. So the main idea is clear, right? I want to maximize kurtosis under those conditions that W transpose W is 1. The norm of W is 1. So we solve this. We want to solve this, and we solve this with Newton method. Okay, so so let Fw be defined as 4 times the expected value plus 2 times lambda W, where we know that y is W transpose Z. This is our estimated independent component. The norm of W is 1. So my first question is, what's the value of this? So we remember that Z is a whitened signal. So expected value of Z transpose is the identity matrix. The norm of W is 1. So this expression will be 1. Good. So this is 1. So the derivative, so we want to solve that this is 0. We will solve that with Newton method. For Newton method, we need the derivative of f. So what's the derivative of f? So you can help me. It's 12 times the expected value of W transpose Z to the 1, 2, 3, 4 derivative 2, right? So I want to calculate the derivative of this expression here with respect to W. So it's V. So I have this 4 times 3, that's 12, expected value W transpose Z squared. I have Z, and I need the derivative of this with respect to W, that's Z transpose. And what's the derivative of this with respect to W? This last term? So here is one thing. So this is a vector. It's a vector. So I take the derivative of a vector with respect to a vector. So I need to get a matrix. Right. So times the identity matrix. Okay. So now what we do here is we say that this is approximately the expected value of W transpose Z squared, the expected value of Z transpose plus 2 lambda I. So we decompose this. So if you do this in midterm or final, I will be very mad. But if you do this, then you can write journals and you can get famous. Because this is just a very crude approximation, but it works here, it seems. Okay? So we calculated this. Right? So this was 1. And this is 1. So what we get is that it's 12 times the identity matrix plus 2 lambda identity matrix. So the derivative of f with respect to W is a diagonal matrix where in the diagonal everything is the same. So the Newton method, because of that, it will be very simple. We just need to remember in Newton method we need to calculate the inverse of this, but it's a diagonal matrix where all the elements are the same. Okay, so after this, this is the update of the Newton method. The W at the k time step k plus 1 is the W at time step k minus the derivative of f, the inverse of the derivative of f at, we stay at time step k multiplied with this, the function value at wk, right? And we just plug in whatever we calculated. So we already calculated the derivative of f, and we know the original f. We calculated this is the derivative of f. We just calculated this. And this was the original f function. So this is the update rule. And now what you do is that you multiply both sides of this equation with this 12 plus 2 lambda. So this 12 plus 2 lambda goes there. And you got this for the update. And the cool thing here is that this 2 lambda, the Lagrange multiplier cancels out. So we didn't need to calculate it. Because at the end, you will get that a constant times w in the next step is this expression. We can calculate this expression because it's just the empirical average of these quantities. And we know that we don't care about this constant here because we know that the norm of w is 1. So you'd update w with this expression, and then you just renormalize this. So this is the first IC update for one component. And then you do this iteration. Just one final moment. So what can we do if we want to estimate the second independent component as well? The problem, if you do this again, then you might converge to the same quantity. You want to avoid that. But what you can do is that we know that W is an orthonormal matrix. So you do these updates that we discussed, but at the same time, you want to make sure that your W that you estimate, that will be orthonormal to the previous ones. And you can do like a Gram-Schmidt decorrelation if you want. So let's just come here. So if you already estimated, say, W1, WP, then for the P plus 1 component, you can just say that let it be. So you update WP plus 1 with that update rule that we just discussed. And after that, you have to make sure that this WP plus 1 will be orthonormal to the previous ones. So you calculated this from ICA update, first ICA update. And then you make sure that it's orthonormal to the previous one. So you do a Gram-Schmidt decorrelation. So what's the projection of WP plus 1 to the previous components? That's this. So you just remove. So you estimate WP plus 1 with the first IC update, and you remove the contribution from the previous components to make sure that WP plus 1 will be orthonormal to those guys.
Why did you get WP plus 1 to be linearly dependent on the other ones? So when you remove all the influences, you get 0.
Right, then you have to restart from another random component. Another thing you can do, the problem with that it's not even a symmetric update, right? So you go one by one, you update the components one after one. But you can do a symmetric update too, that you update your components with this first IC update that we discussed. You do one step, and then you do a new update that's like this. So you update all the components, just do one update with first ICA. From that, you make a matrix that won't be orthonormal, but you substitute them here, and that transformation will make them orthonormal, where this you calculate this from the singular value decomposition of this. So if the singular value decomposition is of this is u d u transpose, then this will be u d the inverse square root of that u transpose. Okay, so I know it was fast this time, but there are very good tutorials. So if you get lost somewhere, then you can check the details there, or you can come to my office hours and we can chat more about that. So that's for now. So have fun.